Chapter 11, Part 1, Nomenclature and Physical Properties of Alcohols and Ethers. First, we're going to review alcohol nomenclature. This is something you have learned before, so we're going to go through pretty quickly. Remember that the IUPAC format for an alcohol name takes the format of alkanol, where you're saying the main family name of the alkane and then finishing it with "all." Remember that if you have a double bond or a triple bond or you have any substituents, those things are all going to appear in this portion of the name. So you would possibly change your infix. You might have some extra substituents up at the front, but overall it needs to end in OL. The common naming is alkyl alcohol. So methanol, for example, is an IUPAC name, but methyl alcohol is the common way of naming methanol. So in this one, you're just taking the alkyl group and then saying the word alcohol afterwards. Some other names that you already kind of know, ethanol, ethyl alcohol. Remember, we're usually sticking to IUPAC in this class unless common is specified. 2-propanol is the same as isopropyl alcohol. 2-methyl-2-propanol is tert-butyl alcohol. So let's go ahead and practice some naming. Pause for a second and see if you can come up with the names of these compounds on your own. So let's take a look at the first example. We have an alcohol group and we have an alkene, so you need to think about your priorities here. The alcohol is going to be more important than the alkene, so we're going to number from the right to the left. So this is going to be a propanol, and then we just need to make sure that we indicate where all the different things within the molecule are. So we have an alkene starting on carbon 2 and our alcohols on carbon 1. So we could call this prop-2-ene 1-ol. You could call it 2-propene 1-ol. This compound also has a common name of allyl alcohol. So let's take a look at our next example. This one, you might have come up with the common name really quickly. The common name for this one is benzyl alcohol. That one's kind of easy to remember because we know that this is the benzyl group when it has the CH2 in between the benzene ring and whatever else you're talking about, so benzyl alcohol. But if you were to name this in the IUPAC nomenclature, the methanol portion is actually the most important thing, and then this becomes a phenyl substituent because it will no longer include this carbon. And so the IUPAC name for this is actually phenyl methanol, all one word. Let's take a look at our next one. This one has a common name that is generally accepted. So this compound is usually called phenol. It does technically have an IUPAC name that is benzenol, but typically it's called phenol, and that name has actually been accepted by IUPAC and is often used as part of IUPAC names. So as we move over to our next compound, we can actually name this as a derivative of phenol. So we assume that this is carbon number 1 because of the alcohol, 2, 3, 4. We can call this 4-methylphenol, and this is the correct IUPAC name for this compound. When you get to OChem 2, you're going to learn about ortho, meta, para substituents on benzene rings. But for now, know that this can also be called p-methylphenol, the P standing for para. This also has a common name, though this is not on a list of things that I would ask you to memorize, but it can also be called paracresol. So benzenes that have a methyl and phenyl substituent have the common name cresol, and the P gets swapped out depending on their relative positions to each other. Okay, let's do another set. None of these have any bizarre benzene-based names that you might not know, so this is something that you can pause and work on your own. Okay, let's take a look at the first one together. So there's a couple things that are maybe just slightly tricky about this one. So first of all, you have to be able to recognize that C6H5 is a benzene ring. And then you have to recognize that even though the benzene ring is larger than this carbon chain, the aliphatic carbon chain actually has an alcohol group on it. So that's going to make it the priority, and we need to start numbering from left to right. So then this just becomes a substituent, specifically the phenyl substituent, since there is no CH2 group between carbon 4 and the benzene ring. So we would call this 4-phenyl 2-pentanol. And a quick reminder, the 4-phenyl is obviously referencing the phenyl group on carbon number 4. The 2 is indicating which carbon the alcohol is on. Pent is indicating that there are 5 carbons in the largest chain. The AN infix indicates there are no double bonds in this 5-carbon chain, or triple bonds. And then the OL ending indicates that we have an alcohol. You could also call this 4-phenyl pentane 2-ol if you would like to. Okay, let's take a look at the next one. So we have an alcohol and an alkene in the same molecule. Again, alcohols are a higher priority in naming than an alkene, so we're going to give that the priority when we number. So we'll number from left to right. So we just have to be careful about how we arrange our information here, because we have an alkene that starts on carbon number 4, so we're going to have to reference that within the name. That's going to give us an EN infix. So there are a couple ways that we could arrange this information. We could do pent 4-ene 2-ol if we want, or we could do 4-pentene 2-ol. The important thing here is that you're going to have to put the number of the alcohol in front of the OL suffix, because if you put both the 2 and the 4 out in front, it makes it unclear which piece you're talking about. Also, putting the 2 out in front, even if the 4 is in the middle of the name, is still kind of confusing. So remember that an IUPAC name should always be as clear as possible. So for that reason, I would probably go with the top one usually, because it's very obvious that by this name, I mean that the alkene is on carbon number 4 and the alcohol is on carbon number 2. Okay, let's take a look at the last one. So we have a cyclohexane ring, and it has a couple things going on. It has an alcohol, it has a methyl substituent, and it has an alkene. So the alcohol is the highest priority. The question is, do we want to number from left to right or right to left? Or I guess rather clockwise or counterclockwise. So we can check ourselves real fast. If we number clockwise, we hit the alkene and the methyl group at 3. But if we go counterclockwise, 1, 2, 3, we hit the alkene at 4 and the methyl group at 5. And since the main rule of the IUPAC nomenclature is that you want the lowest numbers possible, we're going to use that first numbering scheme. So 3-methyl, and then remember to include cyclo, hex, 3-ene, 1-ol. You could also leave out the 1 because the alcohol is automatically number 1. So you could also have done 3-methyl cyclohex 3-enol. You also could have done 3-methyl 3-cyclohexene all if you wanted to. I think it's a little more clear this way or this way. Okay, let's talk about nomenclature of ethers. So ethers also have an IUPAC and a common process. So the IUPAC format is that it is an alkoxy alkane. So we view the smaller portion of the ether as an alkoxy substituent on the larger alkane. The common approach is alkyl ether. And that one's much easier to explain with an example. So let's take a look at our first one. So if we look at this, we have two carbon situations here. We have the ethyl group on the left-hand side of the oxygen and the methyl group on the right-hand side. The ethyl group is bigger, so we're going to consider this a derivative of ethane. So we have a methoxy substituent. Methoxy comes from one carbon and oxygen. Just like we talk about like methoxide or ethoxide as nucleophiles or bases. And they are substituents on ethane. So this is methoxy ethane. Now the common naming takes your two alkyl groups, alphabetizes them, and then follows it up with ether. So even though the methyl group is smaller and was part of the substituent in our IUPAC name, we're going to put the ethyl group first and say call this ethyl methyl ether. Now in our next one, we have two equivalent alkanes. So one is going to have to be a substituent on the other. So let's say that we have ethane and we have an ethoxy substituent. This becomes ethoxy ethane. And then for our common name, we're going to have to bring in a little bit of our IUPAC rules here. We don't want to call it ethyl ether. It's much more straightforward to call it diethyl ether. So we're going to bring in the IUPAC prefixes for multiple of identical substituents. Now, diethyl ether is so common that it's also sometimes just called ethyl ether. And it actually has kind of an interesting history as far as anesthesia goes. So ethoxy ethane has a very low boiling point and it puts off a pretty large amount of vapor. And you can actually use this to knock somebody out. Not necessarily for nefarious purposes, but I mean more like back in the olden days before modern day anesthesia was developed. Ether was used to knock people out because the vapor density is so high that there's you can actually force somebody to inhale only the vapor and no oxygen, which will cause them to pass out. So yeah, interesting fun fact there. Let's take a look at this next one. So this next one has two different things going on. We have a T-butyl group, and we also have a phenyl group. The question is, which one is a substituent on the other? This one is a really good example of when the common name is much easier. But if you wanted to go the IUPAC route, you have to remember that in the case of cyclic structures, if the cyclic group is larger than the alkane, you consider the cyclic group to be the base structure, unless there's some extenuating circumstance like an important functional group on the alkane. In this case, they're sharing the oxygen, so the benzene can have it. Now remember that tert-butyl has a kind of complicated IUPAC name, which is 1,1-dimethyl ethyl. But in this case, since it's an ether, we're going to go with ethoxy. And then you follow it up with benzene, but I ran out of space there. So 1,1-dimethylethoxybenzene. You could also call it tert-butoxybenzene. That's a little bit borrowing from the common nomenclature. Or you could go with the full-on common nomenclature, which would be, we have a tert-butyl group and we have a phenyl group. Remember that tert does not count as far as alphabetizing, and so we'd put phenyl second and tert-butyl first. So butyl, phenyl, ether. Okay, fortunately the rest of these are pretty straightforward. So the next one down, it's pretty obvious which chain is the longest, and then we have a methoxy substituent. So the easiest name for this is the IUPAC name, I think. So this is 2-methoxypentane. If you look at the next one, the longest continuous carbon chain here is ethane, even though this molecule looks quite a lot larger. Oops, I just drew a circle I'm not allowed to erase. That's okay. And then we have 2 methoxy groups that are both substituting onto the ethane. So the best name for this would be 1,2-dimethoxyethane. Dimethoxyethane also has some fun common names. So you may or may not recall from when we first learned about diols that a diol derived from ethane in the 1,2 position like that is called glycol. So a common name for this is dimethyl glycol. It also has some kind of weird extra names here, which are glyme and monoglyme. So sometimes you might see the word glyme being used, and it's really just saying that this is present typically as a solvent, as an inert ether solvent. So something that's polar but doesn't have protons that can hydrogen bond. So just kind of interesting and good to know, because I do believe I've seen that on the homework once or twice. Okay, let's take a look at the nomenclature of cyclic ethers. The nomenclature of cyclic ethers is something that you're not going to be tested on too much, but sometimes you will hear some of these words used. So they have a pretty straightforward nomenclature, which is actually pretty easy to do. So you reference that it's a cyclic ether by using the term oxacyclo, and then you count the total number of pieces within the ring, and that's 3, and you call it propane. So even though only 2 of them are carbon, the oxacyclo part tells us that one of those is oxygen. And this has a common name of ethylene oxide, which you'll hear pretty regularly. The common name for cyclic ethers, well, specifically for an epoxide, actually, which is what this is, comes from the alkene that it can be synthesized from. So that's something that we'll get to, I believe, in part 3 of this chapter. So then the next one would be called oxacyclopentane, because there are 5 members of the ring. This is often also called tetrahydrofuran, which is something you've heard of a lot. You know it probably more as THF. So furan is this compound, and if you add 4 hydrogens, tetrahydro, to each over the alkenes here, you end up with this compound, which is where the name tetrahydrofuran came from, and it's definitely the more common name for this compound. Okay, so what do you do if there are two oxygens taking up space within the ring? Whoops, let's try that again. You just indicate their relative positions to each other. So we were to number the rings starting at the oxygens. We would give the oxygens the positions 1 and 4. So this would be called 1,4-dioxycyclohexane. And this has a common name of 1,4-dioxane. Just like THF or tetrahydrofuran, this is a pretty commonly used solvent because it's polar, but it also has those hydrophobic carbons. So it can dissolve quite a lot of things, and it doesn't bring any protons with it, which is useful in a lot of organic reactions. Okay, quick refresher over the physical properties of alcohols and introducing some physical properties of ethers. So remember that alcohols tend to have a higher boiling point for their molecular weight when you compare them to an alkane of similar size. So this diethyl ether here has 5 total members. Its molecular weight is pretty equivalent to that of pentane, but the boiling point is quite a bit higher than that of pentane. Oh, sorry, I'm talking about alcohols and I circled the ether. Hop down to this guy, 1-butanol. Anyway, boiling point of 117.7, whereas the boiling point of pentane here is 36 degrees. So they're really close in molecular weight, but their boiling points are drastically different. And that's going to be because alcohols, first of all, are polar and alkanes are not, but they also have hydrogen bonding. And remember, hydrogen bonding is a really, really strong intermolecular force. So if you have hydrogen bonding, you're going to have a higher boiling point and a higher melting point. Remember that your smaller alcohols tend to be soluble or miscible in water, and they are polar protic solvents. Ethers also have, you can look at an ether that has a similar molecular weight to an alkane, and what you'll see is that they actually have similar boiling points. So they're only slightly different from each other, and ethers are actually a little lower. Now, they do have dipole-dipole interactions that alkanes do not have, but they have 0 hydrogen bonding with themselves. They can hydrogen bond with other polar protic molecules, so if you were to mix these two together, it would actually be a lot more difficult to boil off the ether than if it was just ether on its own. But when ether is alone, it tends to have a pretty low boiling point, and they are polar aprotic.